Now we're homeward bound from the Arctic ground, sailing down to old Maui. Okay, looks like we're live. Excellent. So, Chapter 8, we are beginning to discuss thermodynamics, which is why chemical reactions happen, as opposed to how. So, first off, we need to talk about energy. Okay? Energy is one of those really, really abstract things. Okay? In math, it's the integral of force across distance, meaning that you apply force in the direction of motion, then you're doing work. There's energy involved in that. Let's try an inductive approach. Let's talk about different kinds of energy to see if we can't build that up for you. Okay. First up, we have kinetic energy. Okay. This is the energy of motion. So kinetic energy is equal to 1/2 mv squared, where m is the mass of the object and v is the velocity. So if you double the mass of something, then it'll have twice as much kinetic energy. If you double the velocity, it will have 4 times as much kinetic energy. So the faster something's moving, the more kinetic energy it has. Then we have thermal energy. Okay, this is the energy of temperature. Okay, this is the random kinetic energy of all the particles in an object. The hotter something is, the faster its particles vibrate. Okay? They're bouncing around all over the place. The particles, atoms, are always in motion. And the hotter something is, the higher its temperature, the faster those particles are moving. So the thermal energy is the random kinetic energy of all the particles in an object or a substance. Potential energy is the energy of position. It has the potential to turn into kinetic energy. There are lots of different ways you can get potential energy. So there's gravitational potential energy. That is the position of an object in a gravitational field. Okay, you lift something up, you are working against gravity. Okay, you're putting energy in order to move it up in that gravitational field. You let it go, it will fall down that gravitational field, and it will the potential energy of the height of the object will turn into kinetic energy as it falls. Similarly, you can have magnetic potential energy, okay, due to the position of a magnetic object in a magnetic field, or electric field, with an electrically charged object existing within an electric field. But it's not just the position of things in space. Sometimes it's the substance itself. So an elastic potential energy is when you stretch or bend or twist an object. And you deform it away from its normal shape, it will want to return to its original shape. So long as it is deformed, then it has that elastic potential to turn back into its original shape. You also get chemical potential energy. This is the energy stored in chemical bonds. So hydrogen and oxygen, in their elemental state, are high potential energy, and then they react and they lose that potential energy when they react and make water. So water is much lower in potential energy, and that potential energy that was stored in the hydrogen and oxygen is released as, well, an explosion, basically. You can also have nuclear potential energy. An unstable nucleus will want to decay. And when it does, it will release some particles, obviously, but it turns into a different substance. And that substance will typically be more stable. It'll be lower in potential energy. And eventually, this decay will happen over and over again until it reaches a stable, low energy state. So potential energy is energy that is stored in some way, and it's waiting to be transformed into motion or heat. Okay? And when it is released, then the substance or the energy or what have you will fall, sometimes literally, down the slope of the potential energy field. Okay? We often talk about energy in that way. When we're talking about gravity, then it literally is falling. But we talk about things having high potential energy and low potential energy, and things falling from a high place to a low place, even when it's something like chemical energy. So hydrogen and oxygen have high potential energy. Water has low potential energy. When they react, then they fall down that energy slope. And we often also talk about energy landscapes, even when that's not literally what we're looking at. Okay, calm down. There we go. All right, so you can have I mentioned in class, you have CH4, CH3OH, then acid, formaldehyde, then formic acid, and then finally CO2. We can, this is, remember the oxidation going from methane to carbon dioxide. And you can sort of map that, as a potential energy landscape where you have methane really high up here and CO2 really low down there. Okay. Well, methane, we would love to be able to, store and transport and use that as an energy source because it's cheap, it's light, it's readily available, and it's high in energy. But it's too dangerous to transport. What we would love is if we had a way to turn methane reliably into methanol, because methanol is only slightly lower on that potential energy landscape. The problem is that it is, so steep, this slope. If we were to like this, it's just we can't really get a stable stopping point. Once we start oxidizing the methane down to methanol, we can't really get it to stop. The ball just keeps on rolling, as it were. So we often talk about potential energy landscapes, and sometimes they're easy to map, and sometimes they're not so easy to map. But they're usually there. We like putting things in this rather physical way. This is just a natural human tendency, and it works pretty well for this. All right, so sun to you to poo. Actually, it ends as heat, but so the sun has a lot of energy because of gravity, basically. The material that is now the sun was once free, and it fell gravitationally in and became the sun. And now that gravitational force is pushing really, really hard on the substances in the core of the sun and forcing them to fuse together. And this actually makes those substances nuclearly more stable. The most stable element in terms of nuclear energy is actually iron. So hydrogen fusing into helium, and then you get lithium and beryllium and boron and carbon, all those other elements. Every time it fuses like that, it actually releases a little bit of energy. And that gets released as heat, which turns into light. The light travels across, space, eventually, runs into the earth, and, sometimes it hits a plant. And the plant uses chlorophyll to transform that photon of light, the energy of that photon, into chemical energy, sugar. Then, we eat, whether it's the leaves or the fruit or what have you, and we transform that through metabolism into a different form of chemical energy, ATP, adenosine triphosphate, just a little chunk, a little carrier of energy that our body uses. And then, as you move around and walk and work and fart and so on, that energy is again transformed and used and eventually released as heat. So you have this really high energy light coming in from the sun, and it just keeps on falling down these different slopes as it gets used over and over again by living organisms, and eventually is radiated back out as low energy, high entropy, we'll get to that later, heat. All right. So the unit of energy is the joule. Okay? 1 joule is equal to 1 Newton meter. That is to say, you apply 1 Newton of force across 1 meter of distance. A Newton is kilogram meter per second squared. That's the amount of force necessary to accelerate a 1 kilogram object by 1 meter per second squared. This is all kind of esoteric, but the joule, 1 joule, is the amount of energy needed to lift an apple from the floor to the counter. Okay? It's not a lot of energy. It's a pretty small amount of energy. Or, conversely, when the apple falls from the counter back onto the floor, it will release 1 joule of energy. So when you lift up the apple from the floor and put it on the counter, you are putting energy in to the apple. Not really. You are putting the energy into space. Gravity warps space. So the energy is stored in the warping of space between the Earth and the apple. And then when the apple falls, that warping of space, it falls down that sort of three-dimensional gravitational field, and that potential energy is transformed back into kinetic energy. Okay? And you'll have 1 joule of kinetic energy by the time it hits the floor. Okay, so that is the units of the joules. We more often work in kilojoules just because the unit of energy, the joule, is such a small amount of energy. And even a small amount of chemical reaction is enough to release hundreds or thousands of joules of energy. So that is it for this particular set of slides. I'll be back in a few minutes to do the next set of slides when we talk about the first law of thermodynamics. See you soon.